Section 3.3, Product and Quotient Rules. So in the previous section, we saw a couple examples where we had products and quotients and we were looking to differentiate those functions. And I mentioned that we didn't yet have a real rule or, fixed kind of method for dealing with derivatives of products or quotients. And we were forced to multiply out or divide in order to set up the function in such a way that we could get away with just using the rules we already had, the power rule and the sum rule and the constant multiple rule and so on. So here we're actually going to see what is the product rule, what is the quotient rule. It isn't just as simple as the derivative of the first function times the derivative of the second function. It's a little bit more involved than that, but not too bad, so let's have a look. The product rule. If f of x and g of x are differentiable at x, then so is their product f of x times g of x. And the derivative is equal to the derivative of f of x times g of x, right? Not differentiating g of x yet, plus f of x times the derivative of g of x. Okay, or using prime notation, it's f prime of x times g of x plus f of x times g prime of x. Okay, so I think of this as, the formula involves a sum. There are two terms here, and each function gets their turn being differentiated. Okay, but we do them one at a time, and then, separate these two products with a plus sign. So for example 1, let's look at this function. We already worked with this one in the previous section. We had to multiply this out, FOIL it out or distribute, however you deal with that. And then we just differentiated term by term. Let's try to take the derivative using the product rule. So I'll call this first function f, and we can call this second function g. So f is the quadratic, g is the linear function. And we want to find the derivative of this product. So let's try this. So our derivative, so d dx of this product, f times g, is going to be f prime of x times g of x plus f of x times g prime of x. So let's do this. So f prime is going to be, and I'll do this in purple, f prime is going to be 2x minus 1 times g of x, which is just 3 plus 2x. Okay, so not differentiating g this time around. Plus, now I'm just going to write f of x, x squared minus x, times g prime. So now it's g's turn to get differentiated, and it's just going to be 0 plus 2. And now I just want to simplify this. So to simplify, I'm going to multiply out, I'll FOIL out these first couple terms here. And let's see what I get. I'm going to get 6x plus 4x squared minus 3 minus 2x. And over here, really, I'm just distributing this 2, so I'll get plus 2x squared minus 2x. And I have some like terms here. I've got 6x, negative 2x, negative 2x, so that's just going to become 2x plus, and then I'll get 6x squared, combining those 2x squared terms, and then the only constant I have is minus 3. I'll rewrite this in general form. 6x squared plus 2x minus 3. Okay, so that's going to be our derivative, which we obtained using the product rule. And if we look back to the previous section, we did this example right here. And this was our answer, 6x squared plus 2x minus 3. So we got the same solution either way. It's up to you how you would pursue this problem, assuming I don't ask you specifically on a quiz or test or something to use the product rule or avoid the product rule. But, eventually it'll just be at your discretion, which rules you use and which is going to be the most efficient kind of route to the correct answer. But they both work. So we'll do some more product rules later in this section and throughout the semester. Let's look at the quotient rule real quick. So we can also take the derivative of a quotient g of x or f of x over g of x, assuming f and g are differentiable. And here is the rule. It's a little more involved than the product rule, but still manageable. So this derivative is going to come in the form of a quotient. It's going to be g of x times f prime of x minus, so we have subtraction this time, minus f of x times g prime of x over g of x squared, like this. And I have a little mnemonic here to help you memorize this. So g of x is the function in the denominator. We're going to call this low. Okay, right? Because it's low down. So that's going to be low. And then this top function up here in the numerator, f of x, we're going to call this high. Right? Because one's high and one's low. So the rule, we can also express it in this kind of silly but more memorable way. This first term up here is the low function times the derivative of the high function. So we can say low d high. All right, and then subtract from that the second term, which is the high function times the derivative of the low function. So high d low. And then in the denominator, this is just low squared. Okay, so the formula goes low d high minus high d low over low squared. Or I've heard low d high minus high d low, square the bottom and away you go. Whatever works for you, I'm good with. Okay, but this is helpful because it actually matters. Remember, subtraction is not commutative. So the order of these two terms is really important, right? You'll get a sign error if you do this backwards. So always remember low d high minus high d low in the numerator. Now for example 2, we're going to find this derivative using two different methods. We'll do it once using the power rule, kind of like how we did in the previous section. We had sort of a similar example. And then differentiate the same function but using the quotient rule. So power rule, since we have a sum in the numerator, we can break this up into two separate fractions, right? Like a sum of two fractions. So I could rewrite f of x as 7x to the fourth over x to the third plus 1 over x to the third, like that. And then simplifying these a little bit, rewriting them in such a way that the power rule will be easy to apply. I can rewrite this as 7x to the first power plus x to the negative third power. Okay, so that's just how I'm rewriting f of x. Now to actually find the derivative, I can just use the power rule. So f prime of x will be just 7, right? Because the x will go away with the differentiation, and then minus 3x to the negative fourth power. Just applying the power rule. And I can simplify this. I can rewrite it as 7 minus 3 over x to the 4th. That's one way to write it. Also, if I, choose to write it as a single fraction, I could get common denominators, just involve multiplying top and bottom of this function by x to the 4th. So I could also write this as 7x to the 4th minus 3 over x to the 4th. Okay, so either of these works. Now let's try and find this derivative by using the quotient rule. So remember, the top function is the high function, bottom function is low. So the derivative, in this case, I don't have to do any prep work. I can just jump right into finding this derivative. So f prime of x is going to be, there's our formula, low d high. So that'll be x to the 3rd times the derivative of the top function, which will be, let's see, 28 x to the 3rd plus 0. Okay, so that's low d high, minus high d low, so 7x to the 4th plus 1, so that's high. Now the derivative of the bottom is just going to be 3x squared. Divided by low squared, so that'll be x to the 3rd squared. So now we just got to simplify. I'll get 28 x to the 6th minus, and then distributing this 3x squared to those terms there. Okay, so minus 21 x to the 6th plus 3x squared. All right, and be sure to keep parentheses over here because, when we're subtracting polynomials like this, we have to be careful, make sure we distribute that negative sign when we do that subtraction. And down here we'll have x to the 6th power. All right. Now simplifying a little bit, we are going to get, subtract the 28x to the 6th, or here I'll write out one more step, 28x to the 6th, and then distributing that negative, minus 21x to the 6th, minus 3x squared, all over x to the 6th. So I'm going to get 7x to the 6th minus 3x squared over x to the 6th. Simplifying a little bit, I have a common factor of x squared in the numerator. So I'll pull out the x squared, and I'll have 7x to the 4th minus 3 up top, divided by x to the 6th. And then I can simplify a little bit. I can cancel 2 copies of x with 2 copies down here. And I'll be left with 7x to the 4th minus 3 all over x to the 4th. Okay, so now you can see why I did this extra step of rewriting it in this form, just so we could see that we truly did get the same answer, employing these 2 different techniques. It's up to you which one to use in most cases. For this one, there's more prep work, setting it up for the power rule. Here, there's a little more work simplifying. So maybe I would choose the power rule over the quotient rule in this case, but there will be many situations in which we're forced to use the quotient rule. We're not able to use the power rule. And the next example, number 3, is an example of that. So for 3a, we want to differentiate this function here. So we could break this up, into a sum, like 2x over 3x plus 5 minus 1 over 3x plus 5, kind of in the way we did that previous example. But in this case, since we have a sum in the denominator, there isn't going to be any nice cancellations or simplification. Now we just kind of have doubled our issue, right? Now we have two quotients that we would have to deal with. So I'd much rather only do one quotient rule rather than two. So this is a situation where we truly need the quotient rule to find this derivative. But it's okay, it's not a huge deal. There's our high function, here's our low function. So let's apply the formula here. So f prime of x is equal to low d high, so that'll be 3x plus 5 times the derivative of the numerator, so that'll just be 2, minus high d low, so 2x minus 1 times the derivative of the bottom, which is 3, and then square the bottom and away we go. So 3x plus 5 squared. So I'll simplify, I'll distribute in this 2, I'll distribute in this 3, I'll also distribute in this negative 1 so that we can, do the subtraction. So we'll get 6x plus 10 minus 6x plus 3. All over 3x plus 5 squared. I'm not going to bother multiplying out the denominator at this point, because what if in the numerator something simplifies down to 3x plus 5? Then I would have a common factor. So we usually want to leave it in factored form just in case we get common factors in the numerator and denominator. So I'm not going to bother foiling out that denominator at this time. Okay, but simplifying the numerator, the negative 6x and positive 6x make a 0, and I'm just left with 10 plus 3, so 13 over 3x plus 5 squared. And that's my answer. That's our derivative. And now for what should be part B, I don't know why that says A. For part B, we want to find the equation of the line tangent to that function at x equals 1. Okay, so our answer is going to be in the form y equals mx plus b. I usually start by finding m. This is the slope of the tangent line. And this is just going to be f prime evaluated at 1. So that'll be 13 over 3 times 1 plus 5 squared, just plugging directly into that derivative. So that'll be 13 over 8 squared, or just 13 over 64. Okay, so not the nicest slope I've ever seen, but we can work with that. So there's our slope. Now to find the y-intercept, remember we always need the x-coordinate, the y-coordinate, and the slope. We're only given the x-coordinate here. So first, before I can sort of plug in and solve for b, I need to find what y is. And remember, we are talking about a point that is on the graph of the original function. So to find the y-coordinate, I need to plug into the original function. So y is going to be f of 1. Okay, so I'll have 2 times 1 minus 1 over 3 times 1 plus 5. All right, so it looks like I am getting 1 over 8. Okay, so our ordered pair here is going to be the ordered pair 1, 1/8. Okay, so sometimes we have to do this, if we have a tangent line problem where instead of being given an ordered pair, we're just given the x coordinate. We'll need to find that y coordinate by plugging in, but remember, we plug into the original function, not the derivative. But now that we have that ordered pair, we can find b. Okay, so we're plugging into y equals mx plus b. I'll plug in 1/8 for y, 13/64 for m, 1 for x, and add that with b. Okay, and then here, maybe I'll keep working over here. I'm going to rewrite that 1/8 as 8/64, just because I know I'm going to have to do some subtraction of fractions here, so I'll just get common denominators in anticipation of that. So I'll subtract 13/64 from both sides. And I'm getting that b is equal to negative, what is that? Negative 5/64. So our answer is going to be y equals m, which is 13/64, x plus b, which is going to be minus 5/64. All right, if you feel like checking your work, you can plug the original function into your graphing calculator. For y2, you can plug in our answer, so the equation of that tangent line. And then you can zoom in on that ordered pair 1/8. Make sure they intersect at those points. That's just how you could check your work. I promise you that this is the correct answer, but if I was working on a test and I got numbers like 13/64 and negative 5/64, I might want to check my work. All right, now example 4. We did a problem just like this one in the previous section. Find all the points on the graph of this function f of x, which is a rational function. We want to find all the points where the tangent line is horizontal. So remember, horizontal tangent lines, that implies that the derivative is equal to 0. So we want to solve this equation f prime of x is equal to 0. That's, ultimately what we are trying to do here. The solutions to that equation will be our answers. So let's find this derivative first. I have to use the quotient rule here. There's no way that I'll be able to simplify this down in such a way that I'll be able to use just power rules and sum rules and all that stuff. So I'm going to have to do a quotient rule. This might be kind of a big one, so hang on. So let's do low d high, so that'll be x squared minus x plus 1 d high, so times the derivative of the top 2x plus 1 minus high d low x squared plus x minus 1 times 2x minus 1. And then square the bottom and away we go. So x squared minus x plus 1 all squared. Okay, just kind of checking and making sure I copied down everything correctly, because it'd be a shame to do a bunch of work on this problem just to realize that I wrote a plus sign instead of a minus sign there or something like that. But I think that we are okay. So now I'm going to start simplifying. This is going to get a lot worse before it gets better. I'm going to multiply out these two products in the numerator. So foiling out, or rather, distributing. I think the way I'll do this is I'll take this binomial and I'll distribute it to each of these terms. And here's what I'm going to get. I'll get 2x cubed plus x squared minus 2x squared minus 1 plus 2x plus 1. So that's that first product minus now the second product. Again, I'll do the distribute this binomial into each of those terms there. I'll get 2x cubed minus x squared plus 2x squared minus x minus 2x plus 1. Gonna check that work. I think we're doing okay. All right, and this is still all divided by x squared minus x plus 1 squared. I'm going to leave that in factored form. So, I can combine like terms. I can, to do this subtraction, I'll want to distribute that negative sign over there. I'm going to spare us a lot of that work, and I'm just going to tell you what it simplifies down to. I'm left with just negative 2x squared plus 4x all over x squared minus x plus 1 squared. Okay, so that's my derivative. So this is what I want to set equal to 0 and solve. And the nice thing about this, so I'll say now we want to solve I'll just write it out. F prime of x, negative 2x to the 4th plus 4x over all that stuff squared is equal to 0. The nice thing here is, remember, for a fraction to be equal to 0, we just need the numerator to be equal to 0. So actually, to solve this problem, I only need to set the numerator equal to 0. Oh, sorry, that should have been negative 2x squared plus 4x equals 0. And I can solve this by factoring, pull out a negative 2x, and then in the parentheses I'm left with x minus 2 equals 0. So it looks like my two solutions are going to be x equals 0 and x equals positive 2. All right, the 0 coming from that factor and the 2 coming from that factor. Okay, so same procedure as before, just the derivative in this case involves a quotient rule. But as long as you're really careful and working slowly and not rushing, I trust that you could get through something like this. Okay, and then very last example, example number 5. This is a fun one. We are not actually told what our functions f and g are. We're just given some basic kind of, ordered pairs really for the original function and the derivative. So for f, like if f of 6 equals 11, that just means that this ordered pair 6, 11 is on f, right? And then this ordered pair 6, 5 is on g. Okay, and then what does this mean? F prime of 6 is equal to 9. So the derivative evaluated at 6 is 9. If this were a graphical type question, it might be convenient to think about like, oh, the slope of the tangent line at x equals 6 on f is equal to 9, and so on, right? And then we're given this point for g prime. What we're asked to find is what is f times g prime evaluated at 6. So we're being asked about the derivative of the product of these two functions. So it might be helpful to just start by thinking, what is the product rule? Right? So like f times g prime evaluated at 6. So the product rule is, take the derivative of the first one, so f prime of 6, multiply it by the second function, and we're just evaluating everything at 6 this time, plus f times the derivative of g, and just evaluating everything at 6. All right, so I just expanded out. Sorry, there should have been a little prime there. I just expanded out, using the formula. What is the derivative of f times g evaluated at 6? And this is what I get. And I conveniently have values for each of these, right? I know that f prime, like I'll just highlight all the relevant things. F prime of 6 is equal to 9. G of 6 is equal to 5. F of 6 is 11. And then G prime of 6 is also 9. Okay, so I'll just evaluate these. So this will be 45 plus 99. So I'm getting 144. All right, and it makes sense that our answer is just a numerical value because, yeah, f times g prime is going to be a function, but we're evaluating it at 6. So we would expect this to just be a real number, okay? We're guaranteed that it's a real number since we have that f prime and g prime are both defined, because remember, as long as the two functions are differentiable at whatever value we're looking at, in this case 6, we know that the product is going to be differentiable at 6. Okay, so that brings us to the end of section 3.3 on the product rule and the quotient rule. We've got like one more kind of big important rule called the chain rule. It helps us deal with compositions, derivatives of compositions of functions. And beyond that, we're going to move into some applications of derivatives. We'll talk about implicit differentiation. But that is it for 3.3. I'll see you in the next section on the chain rule.